one last cool example of eddy currents. You know I'm going to love this being from the astrophysics, okay? So Io is this extremely volcanic moon that orbits around Jupiter. We remember Jupiter from our exam, right? Yeah, pretty cool. Maybe making another appearance, we'll see. Okay, so Jupiter's moon Io is slightly larger than Earth's moon. It's bigger than Earth's moon, and it moves at more than 60,000 kilometers per hour through Jupiter's intense magnetic field. It's about 10 times stronger than Earth's field. The magnetic field is 10 times stronger, but because the area of Jupiter is so much bigger, the magnetic dipole is like 20,000 times bigger than Earth's magnetic dipole. So the dipole also plays a role. But anyway, this sets up strong eddy currents within Io. Where do these eddy currents come from within Io, though? Well, the crust might be a little bit magnetic on Io, but we can almost be certain that the majority of this comes from its core because it has an iron core. Most of our terrestrial moons and our planets, like Earth, Venus, Mars, they have like metallic cores. Io has a metallic core. There's eddy currents that are circulating in this metallic core, producing intense amounts of energy that's dissipated that heats Io's interior. So that's why it comes from the interior, because the core is heating, and it comes up, and it causes these massive volcanic eruptions on the surface, as shown in this close-up image. This is an actual image of volcanic eruptions on Io. It's absolutely scorched. This place looks like hell on earth. There's huge volcanoes everywhere. It's all because of the magnetic fields of Jupiter and its proximity to Jupiter, caused by these eddy currents from these induced currents within the core. Because currents carry a lot of heat and they dissipate through resistance. Remember, V equals IR, and we've got this heat associated with the current that heats up the core a lot. Okay, let's take a break, and then when we come back from break, we're going to talk about displacement current and Maxwell's equations. Okay, let's get started now. So we've seen that a varying magnetic field gives rise to an induced electric field. And one of the more remarkable examples of the symmetry of nature, we've got that a varying electric field gives rise to a magnetic field. So if we have a varying electric field, an electric field that is not constant, we're always going to have a magnetic field as well. This was discovered by Ørsted, I believe, in a lab. He was playing around with magnets, and he changed the electric signal, and he noticed that there was a change to his magnets. And Faraday also worked on this as well. This effect is of tremendous importance. It explains how we have light. So, we need to generalize Ampere's law, which we saw. Ampere's law was this convenient little, it looked like a cute little trick for finding the magnetic field for currents or whatever in the last class. But now we're going to see why it's such an epic equation and why it's so important. And it's because we have this relationship between electric and magnetic fields that we can see in Ampere's law. Remember, line integral of B dot dl is equal to mu naught over I enclosed. So the line integral of the B field is equal to like the current that's being enclosed. So if I have a couple of currents going into the board from some wires going this way, and then I draw a thing here, I've got this line integral around here. We've got like a line integral of B dot dl, where I'm summing up. The dot product means I'm summing up all the components of the B field that are going to be, and which my B field, right-hand rule, okay, tells me the direction of the B field. The B field's got values all along this path. And if I make the path smaller, this still works, because what happens is, by a beautiful consequence of nature and geometry, if I make this path smaller, this B dot DL, we could call this B dot DL1, B dot DL, B1 DL1. This is equal to B2 dot DL2. These two line integrals are equal, even though they're different paths and they have different DLs associated with them. The DL is not the same. The B dot DL is the same. Why is the DL not the same? Well, obviously, this is a bigger line, so this is a longer path than this one. But what happens is the B field grows in strength in exactly proportion to the change in the fall off with like length of the path integral. And it doesn't even matter what path it is, as long as it's a closed path, it can be any shape we want. How cool is that? That's amazing. That's why this thing is so cool, because it's maybe not very complicated and it's easy to solve problems, but that's why it's so cool, because it makes things so easy. Well, okay, but we have to do something with it. There's a problem. Ampere's law in this form is incomplete. And the process of charging a capacitor, we can see that. We've got these conducting wires that lead a current I capacitor into one plate and out of the other. The charge increases on the plates of these capacitors. So we have some capacitor here, and charge accumulates on one of the capacitors. And so we have an increasing voltage across the plates of this capacitor, okay? And IC indicates that it's a conduction current, and that distinguishes it from a different kind called a displacement current. We use lowercase i's and v's to denote the instantaneous values of currents and potential differences, respectively, that vary with time. Okay, so let's talk about this a little more. Okay, so we've got a parallel plate capacitor being charged. Let me draw a better drawing of this now. So first of all, let me reverse it. It doesn't really matter, but since I'm going to keep in consistency with the drawing here, we'll have these plates, and we'll make them cylinders, even though it doesn't actually really matter. Not cylinders, discs. So it's a parallel plate capacitor, but it's like a disc type of parallel plate capacitor. Doesn't have to be, though. It could be squares as well. Okay, so I've got these two discs. These are sides of my parallel plate capacitor. Charges accumulate, and there's an electric field between these charges, these charged up plates. And you remember, you charge the capacitor, and what happens to the value of the field? It gets stronger. The electric field grows as you separate these charges, and you produce this electric field. Now we also have a little bit of geometry here. So now we can see why they drew it as a circle, because it fits nicely in this geometrical picture here. So now I've got this volume here, and this volume is associated with this DL. So now you can see I'm going to use this to relate this to Ampere's law. So we've got a DL, and then I've got this current going in, this IC. So current's going in, and it's going all the way to E. Okay, so here's my current, IC. And we've got our DL here. This is the path that we're going to go for Ampere's law. And then we've got this surface, and we've got this plane of the surface here. Plane of the surface. Okay, the capacitor is being charged, and then the current IC is going through here, and then it's going out this way as well. Okay, so the conduction current through the plane surface is IC, but there is no conduction current through the surface that bulges out to pass between the plates. So the two surfaces have a common boundary, so this difference is in I enclosed and leads to an apparent contradiction in applying Ampere's law. So there's a problem with Ampere's law in this situation, because we found a little loophole here. we enclosed the path, and yet we don't have IC going through here. There's IC, you see how it ends right here? There's no IC right here. So there is no conduction current through the surface that bulges out to pass between the plates. So the conduction current dies off and then it goes again on the other side. So how do we deal with this? We need to apply Ampere's law to the circular path. The integral of B dl around this path equals mu naught I enclosed. For the plane circular area bounded by the circle, I enclosed is just the current IC in the left of the conductor, okay? But the surface that bulges out to the right is bounded by the same circle, and the current through that surface is 0. So line integral of B dot dl is equal to mu naught IC, and at the same time it is equal to 0, showing a contradiction. But there's something else happening on this bulged out surface. As the capacitor charges, the electric field E and the electric flux through the surface are increasing. So there's a change in flux through this surface because it's charging and the E field is increasing. And the electric field is also increasing through the surface. So we can determine their rates of change in terms of charge and current because the units are the same. So the instantaneous charge Q is CV, where C is the capacitance of the capacitor. And V is the instantaneous potential difference. So not a velocity, a voltage. Potential difference is voltage. So Q is equal to CV, voltage. I would like a big V better than little v, whatever. For a parallel plate capacitor, the capacitance is also equal to E naught, where E naught is the permittivity of free space from an electric field, times A over D, where A is the plate area and D is the spacing. So we have this potential difference between the plates, and that's given by the electric field times the distance, where the E is the electric field magnitude between the plates, right here. E is that. Okay. And we ignore fringing, and fringing is just things that happen outside the plate, small effects. We ignore that. And we assume E is uniform in the region between the plates. It's constant. So if this region is filled with a material with permittivity E, we replace epsilon naught, which is the permittivity of free space, with epsilon, which is the permittivity associated with this. So now we're going to move from E naught, which is like a constant associated with free space. You could think of it as like mu naught for a magnetic field. It's for electric field. We replace it with this epsilon for the capacitor. It changes. So now we've seen an intrinsic relationship between like the fundamental of nature. It changes a little bit when we have capacitors. Okay, so we substitute this into the expression for capacitance and voltage, and we can express the capacitor charge Q in terms of the electric flux through the surface. So now we have the charge Q is equal to the capacitance times the voltage, which is equal to epsilon, not epsilon naught, but epsilon times the area over D times the voltage, which is the electric field, times the distance separating them. And so then we have some things simplifying. We have, this just turns into EA because the D's cancel. And so we have epsilon EA, and we know that E times area is just phi E. So as the capacitor charges, the rate of change of the Q is the conduction current. Taking the derivative with respect to time, we get that we have the IC here is equal to dq by dt, which is the change of charge with respect to time. We're familiar with that expression, but now we have this new expression, E times d phi E by dt, which is the electric flux through the surface. Phi E is a flux. So the change in electric flux times the permittivity through the capacitance region of this volume is my current. So the ability to support the current involves the permittivity of the capacitor and its changing electric flux. That gives me the current supported through this. And then we invent this fictitious displacement current, ID, in the region between the plates. So we say, okay, there's an imaginary current that connects them. So let's say, okay, you know what? There isn't really a current here, but let's say there is. Let's call it ID. What would happen if there was a displacement current in this region? Well, we have an expression for what the current would be from the capacitor. We just talked about it. It's going to be epsilon times the change in flux of the electric field. So that's going to be our current here, not our IC, but our ID, displacement current. So there's an imaginary displacement current given by epsilon here times the change in electric flux with respect to time. Electric flux due to this electric field, and it's a changing electric field. Okay, time rate of change of electric flux through the area. I want to stress that the entire time this process is occurring, this capacitor is charging. That's why there's a change in the electric field. Does everybody understand what's going on here right now? Yes. Okay, great. So we imagine that the changing flux through the curved, bulged out surface is equivalent in Ampere's law to a conduction current through that surface. We include this fictitious current along with the real conduction current in Ampere's law. So now that I have this current going through here, I also have this fictitious current, displacement current, and then I change Ampere's law to involve that. So now it's not just B dot dl equals mu naught IC, it's B dot dl, line integral of that equals mu naught IC, so line integral of B dot dl equals mu naught, and then we have our IC plus displacement current. And then that's going to be what's enclosed by our surface. Because our surface incorporates this current going to the plate of the capacitor, which we know exists. So that's our first contribution. So we've got this bulged out surface, and right here at this surface here, on one hand, we have IC stopping here and going through here, and then right at this boundary, we have ID. So there's a changing flux due to both of these, because we have current going in and current going out. This one's going in, this one's going out. So we add these two together, and they're enclosed within this surface here. And remember, these are the plates of the parallel plate capacitor, and this is the electric field in there. Okay, so now we have mu naught IC plus ID enclosed. Ampere's law in this form is obeyed no matter what surface we use. So for a flat surface, if it's flat, if this is not curved here, ID is 0. For the curved surface, IC is 0, and IC for the flat surface equals ID for the curved surface. So this equation remains valid in magnetic materials, provided that the magnetization is proportional to the external field. So this was invented by Maxwell, who was working with Ampere's law, and he was trying to figure out a way to make it work. He made up this displacement current, JD, is equal to I displacement over the area. Using the flux, the electric flux as E times A, and we divide by this to find A, we find that this displacement current, JD, is equal to the permittivity of the capacitor times the change in the electric field with respect to time. And it makes Ampere's law work. That's the only reason he did it. He had no measuring device that could measure it. He just inferred that if this existed, we'd actually have Ampere's law would work. But it allows us to also generalize a junction rule from circuits. So if we consider the left plate of the capacitor, we have a conduction current into it, but none out of it. But when we include the displacement current going through here, we actually have conduction current coming in one side and an equal displacement current coming out. So this preserves the conservation of current, also known as the junction rule. Current in equals current out. So this situation without displacement current, this also violates Kirchhoff's laws. That's another important point about this. It's not just Ampere's law that gets violated, also Kirchhoff's. But this brings it back and allows for the junction rule where one current in through one junction equals current out the other. So we can think of this as a junction in a circuit, analogous to a junction in a circuit. Okay. And with this meaning of current, we can speak of current going through a capacitor. So we don't normally think of current. We say, what's the current through this capacitor? It's zero. Currents, that's what makes it a capacitor to begin with, right? There's charges here. If there was a current, actual current going through the capacitor would lose its charge because the current would no longer be accumulating on both plates. So that's how weird this displacement current is. There's no way it could be real, right? Because if there was, the capacitor would lose its charge if charge was accumulating. Assuming that the charge accumulated in this direction, but maybe it doesn't. We're still have to think about this a little more to understand that. Okay, so you can ask whether the displacement current has any real physical significance or whether it's just there to make the math of Maxwell, Ampere's law, and Kirchhoff's work. So here's a fundamental experiment that helps answer the question. We can take a plain circular area between the capacitor plates. And if the displacement current really plays the role in Ampere's law that we've claimed, then there should be a magnetic field in the region between the plates. There should be a B field here as well when the capacitor is charging, because then there's a change in electric field while it's charging, so there should be a magnetic field there as well. And we can use the generalized Ampere's law, including the displacement current, to predict where the field should be. So now we're just looking at this region here in between these two plates. So we've got this region here between these two plates here, and then we draw this little line, circle here, to look at what's going on inside here. And then we call this point here A, and this point here on this circle B. And then there's a radius R associated with this little circle for this little path. And we call this we look at the situation and we say, okay, there's an electric field and a B field there at the same time. How does that work? Well, we've got a capacitor charging the current, and it has a displacement current equal to IC between the plates. With the displacement current density being J, D being the displacement current density, we've got this epsilon times dE by dt. This can be regarded as the source of the magnetic field between the plates. So this change, this displacement current is the source of the magnetic field. And it's going around this way by the right-hand rule. It still obeys the right-hand rule too. Got a B field going around here from this displacement current. Okay? So the capacitor has a displacement current equal to the IC between the plates with displacement current density, JD. And why is it equal to IC? Because it has to be conservation of current. The junction rule, we say Kirchhoff's law generalizes. It has to. So let's picture these round capacitor plates with radius R. To find the magnetic field at a point in the region between the plates at a distance R from the axis, we apply Ampere's law to a circle of radius R passing through the point with little r less than big R. The circle passes through points A and B. The total current enclosed by the circle is the displacement current times its area. So we have I displacement over pi big R squared times pi R squared. And then this integral B dot dl is equal to 2 pi RB, and that's equal to mu naught times little r squared over big R squared. So the ratio of those two R's times the initial current, the IC, and that gives us a B field here that's going to be equal to, so B field that's induced here in this region is mu naught over 2 pi little r over big R squared, because we had an R cancel, one of the little r's canceled there, times IC. So it's proportional to the initial current coming in. This result predicts that in the region between the plates, B is 0 at the axis and increases linearly. So the B field is not constant between this parallel plate capacitor, even though the E field is. That's really interesting. Think about that for a minute. Whoa, we've got a B field that increases linearly with distance from the axis. And similarly, outside the region between the plates, B is the same as though it were a wire and were continuous and the plates were not present at all. So outside of this region, it's like these plates don't even exist and there's a current that just goes continuously if we look at the B field induced from this. So geometrically, we're seeing a very different picture than what we're actually doing here. We're doing something very interesting with the fields. When we measure the magnetic field in this region, we find that it really is there. So there is a magnetic field there. Well, if there's a magnetic field there, then there kind of has to be a current. But that's crazy. So this confirms that the displacement current is a source of magnetic field. Even though it's not necessarily there, it's actually a fundamental fact of nature. It kind of is there. So this is the kinds of things in physics that we love. Because if we find something like this that says our laws of physics say this isn't possible, but then it is possible, then we know we've discovered new physics. And that's what we want to do, right? Like if we want to advance as a species and explore nature, we're never going to get anywhere with the technology that we have now for space exploration. We're going to have to discover something like this, except we're going to have to discover it for quantum field theory instead. But in the 1800s, they discovered this for electric and magnetic fields, and guess what this led to? Cell phones, okay? Devices that generate electromagnetic waves for information, because this led to the realization that electric and magnetic fields are light. So with this breakthrough, this advance in our understanding of nature, we actually progressed forward. This is why physics is so important. I can tell you right now, your life will not change one instant from the moment that you're young to the moment that you're old unless our understanding of physics changes. Our understanding of physics hasn't really advanced very much in the last 50 to 70 years. Hence, all the technologies that you're seeing are just applications of physics that was already known. Einstein and others came up with the concept of the laser in the 20s and 30s. The laser wasn't actually realized as a practical device until like the 60s or 70s. Gravitational waves were thought of in the 1920s by the Einstein field equations. They were just detected by LIGO like 5 years ago. That's how powerful theoretical physics can be in situations like this. We can actually discover things that are otherwise hidden from us, and they would always be hidden from us if we didn't use this mathematical reasoning. That's the magic of physics and the power of physics. Most powerful subject ever. Okay, so now we're in a position to wrap up in a single package all of the relationships between electric and magnetic fields and their sources. And we've got 4 equations called Maxwell's equations. Maxwell did not discover these equations, but they're named after him because people are so impressed with this displacement current and how he figured out what the displacement current was that they named him after him, because he unified them. And actually they were 20 equations, and Oliver Heaviside unified them further into 4 equations, and he usually gets totally left out of the discussion. He gets screwed by the greediness of the historical tale. But he did a lot too to advance these. The equations that you see, Maxwell's equations, they are given by this. We have Gauss's law for electric fields. We have an integral of E or B over a closed surface. This is Gauss's law for electric fields, and we have Gauss's law for magnetic fields. The closed path integral of B dot dA is equal to 0. Why is that? Because there's no monopoles for magnetic fields. I put that on your exam as a challenge question, right? We can't have magnetic charge always has two, north and south. So any flux through a surface, a closed surface, is always going to be 0. And conversely, the line integral of B dot dA is always going to be 0 because of that same fact. Now, we also have that, among other things, magnetic monopoles, just like I said. There's a third and fourth equation that involve a line integral of E or B around a closed path. Now, these equations look pretty simple, but think about how complicated this is. On one side, you have an integral, and on the other side, you have a differential. These are nasty differential equations to solve in certain cases. This is not a simple operation. Figuring out these relationships for these fields and everything else, it's easy now, but it took people 20 or 30 years of intense study every day to get it in that form. Heaviside worked on it for decades, okay? And then, so the third and fourth equations involve a line integral of E or B around a closed path. Faraday's law states that a changing magnetic flux acts as a source of electric field. We saw it here with the displacement current. Now we're seeing it in its final form. The negative of the time rate of change of magnetic flux through a path equals the line integral of the electric field around the path. Thus, a changing magnetic flux is a source of electric field, and there is a changing magnetic field which must be carried out over a stationary closed path, and it's not 0. Thus, the E field produced by a changing B is not conservative. That's the reason for that. So the fourth and final equation is Ampere's law, including the displacement current. So now we actually take this displacement current, and not only do we infer that it exists, we actually put it in the actual equation, even though you can't really measure it with a galvanometer or whatever. Actually, you can sort of if you measure the magnetic field, but it's not like a current in the normal sense. Okay, so this equation, Ampere's law, states that both a conduction current and a changing electric flux act as sources of a magnetic field. So there's a lot going on here. We've got a line integral of a magnetic field around a path. We've got a magnetic constant here. We've got our current. There's a conduction current, and then there's this displacement current that's expressed in terms of the change in electric flux. So we don't write little ID there because we still don't like that. We're like, it's imaginary, we can't measure the current, but we can measure the change in flux. So instead of writing the law in terms of the displacement current, we take the displacement current expression and we write it for the change in the electric flux. But that is the displacement current through the path. It is. That's where that comes from. It never would have been discovered without that theoretical device, that thought experiment by Maxwell. And, Einstein, this is who Einstein was like always looking up to when he was doing his work. He was a massive fan of Maxwell. That was his, Maxwell and Faraday both. But he had pictures of him always in his office because he was so impressed by this thought experiment that Maxwell did with the displacement current. It inspired him to do his own thought experiments and imagine situations that seem silly and impossible, but maybe they could be useful for mathematical ideas, and they were. So we can look at the electric field and its role in Maxwell's equations. In general, the total E field at a point in space can be the superposition of the electrostatic field caused by the distributions of charges at rest. So we have an electrostatic field and a magnetically induced non-electrostatic field. So the magnetically induced electric field is non-electrostatic, and that's the total E field. The E field is that due to the charges and to the induced electrostatic field from the B field, inducing an electric field. The electrostatic part is always conservative. Line integral of EC.dl is 0. This conservative part of the field does not contribute to the integral in Faraday's law, so we can take it out, and we can take the total electric field, including the part for EC due to the charges and the magnetically induced part. The non-conservative part of the field does not contribute to Gauss's law because this part of the field is not caused by static charges. Gauss's law only applies to static charges. So hence, line integral of En.dA is always 0. We conclude that in all of Maxwell's equations, E is the total electric field. These equations don't distinguish between what's conservative and what's non-conservative. They don't care whether it's a conservative or non-conservative. They just care about the total E field in general. So our principle of superposition for a vector field applies to the electric field. Whether it's electrostatic or not, the two fields combine linearly and obey linear superposition. Thus, they can participate in the same vector equation. That's critical. In order to write vector equations for fields, we have to obey the principle of linear superposition. That's a basic concept for vectors that has to apply, and we have that. So there's a symmetry in these equations. In empty space where there's no charge, the first two equations are identical in form, one containing E and the other containing B. Those are just Gauss's law for electricity and Gauss's law for magnetic fields. When we compare the second two equations, there's a changing magnetic flux that creates an electric field, and the other one says that a changing electric flux creates a magnetic field. So in empty space where there is no conduction current, the two equations have the same form apart from a numerical constant, with the roles of E and B exchanged. So in empty space, there's no charges, so there's no charges at all. But look, we still have currents, well, not currents, we still have fields, even in empty space. Now, this is the abstract part where we're really jumping into like the next level thinking here. So now Maxwell really gets ahead of himself and says, wait a second, we've got these situations. What about in free space? What do these equations tell me in free space? Well, in free space, I still have this change, this E.dl is this change in B field, and then I have this B.dl is this change in E field. Look at the symmetry there. The derivatives, they're only separated by a sign. So in empty space, there are no conduction currents, so the line integrals around any closed paths are related to the rate of change of flux of the other fields. And we can write these in a different but equivalent form by introducing magnetic flux as B.dA and electric flux as E.dA respectively. And then in empty space where there's no charge or conduction current, IC equals 0, Q enclosed equals 0, and then we have this form, the integral form of these equations. So now we have an integral, and look, they're looking even more symmetric. E.dl, the integral of that is equal to minus d by dt of the total integral of the area, B.dA, the dot product between B and the area vector. Same thing for electric field. The B.dl is the dot product between E and the area vector associated with that, the time rate of change of the integral. So yeah, that's something you don't see in basic calculus, a derivative of an integral, okay? That's a little bit interesting, but you need it for physics. Nature gets that complicated. So there's a symmetry there. There's a time-varying field of either kind produces a field of the other kind in neighboring regions of space. Maxwell recognized these relationships, and he thought, okay, I've got this B field changing that produces an E field, but then I have an E field changing that produces a B field. And he basically figured out, hey, that's light. Light is this changing field. And so that's what it is. These electric disturbances, electromagnetic disturbances, are time-varying electric and magnetic fields that propagate from one region of space to the other, even if no matter is present in the intervening space. And these disturbances are caused by electromagnetic waves, and they provide the basis for light, radio, and television waves, and X-rays. So there we go. We have light coming about because even in where there's no charges, we still have fields. And if we have a changing, oscillating E field, that produces a B field. But that B field changes in proportion to it and reinduces the electric field. Now, light in actuality is a bit more complicated than this. This is only one aspect of light. This is the wave aspect of light. Light also has a particle aspect. In reality, light is neither a wave nor a particle. Light is a fundamental gauge boson field for the electromagnetic force, okay? That's what it actually is. But in this class, we're just going to talk about the classical wave-like properties of it. And for a long time, because water has to propagate through a medium, the water wave, the height above the surface that the wave travels, has a medium, the water itself. So the wave, if we just look at the wave, that's the change in the height or the field. If the water wave is a field, you could say, okay, that's going to be my wave, and then my medium is water. They thought that there was a medium called an ether, and then Einstein came along and said, hey, you know what? I don't think there actually is one, and that explains some things. But we're getting ahead of ourselves, so I won't go into any more detail about that for the time being. But just know that now we can add an equation for the force due to a electric and magnetic thing. And this is the Lorentz force law. So the force on a charge due to electric and magnetic fields is F is equal to QE plus QV cross B. So all we did here was we took our classic equation for the force felt by a charge from an electric field and combined it with a magnetic field. That was actually in the first chapter, but I didn't put it on your exam because we didn't talk about electric fields. But now it's fair game because we talked about electric fields again. Okay, so we have the fundamental relationships of electromagnetism. Maxwell's equations would have even greater symmetry between the E and B fields if magnetic charges, magnetic monopoles existed. The right side would contain the total magnetic charge enclosed by the surface, and the right side of the other equation would include magnetic monopole current terms, but no magnetic monopoles have ever been found. And in conciseness and generality, Maxwell's equations are in the same league with Newton's laws of motion. This is, yes, they're absolutely very important, and this was a major achievement. So, that's all we're going to have to say about Maxwell's equations. There's a symmetry, electric fields, changing electric fields induce magnetic fields, changing magnetic fields induce electric fields, and the two work together to produce propagating light. Now we're going to talk about inductance. This is the next chapter, just a little segue into the next chapter here. Inductance is this property where a coil of a wire behaves differently in a circuit than the same wire that is straight. So coils we have like a coil of a solenoid or something. I won't bother to draw it out, but we can just think about it for now. They increase the voltage for a circuit. So a 12-volt car battery can give thousands of volts to the spark plugs. So how does this work? It works through inductance. A change in current in a coil induces an EMF in the adjacent coil. It goes right along with Maxwell's equations. The coupling between the coils is described by their mutual inductance. So a change in current in a coil also induces an EMF in that same coil. And this is an inductor with a self-inductance. If a coil is carrying a current and that current decreases, energy is released while it decreases. So we have two concepts with inductance in circuits. We've got self-inductance of the inductor by itself, and we have mutual inductance of two inductors in some kind of a circuit. So mutual inductance, a change in current in a coil induces an EMF in the adjacent coil. The coupling between the coils is described by their mutual inductance. A change in current in the coil also induces an EMF in that same coil. And these coils are called inductors. And the relationship of current is described by inductance, also called the self-inductance of the coil. If the coil is initially carrying a current, energy is released when the current decreases. This principle is used in ignition systems. And we find that this released energy that was stored in the magnetic field caused by the current that was initially in the coil. So this is fascinating. So we have this inductance property where we have the magnetic field actually stores energy. Okay, how does magnetic field store energy? If you take some air track gliders and you take them and you put magnets on them, you'll notice that the magnetic field can push the other one away. And we can take kinetic energy, right? We can take two air track gliders. I should just try to get one of these set up in this classroom because this would be useful. They both have magnets, right? Like north-south, north-south. And we put them on some track and they're going towards each other. What happens is if I push both of these magnets, they have some kind of energy, 1/2 mv squared, right? 1/2 mv squared. They're both coming at the opposite direction with some kinetic energy. The kinetic energy is a scalar because the velocity is just a scalar, it's squared. So it doesn't matter. One of them's going this way, one of them's going this way. What happens when these two magnets come together? The magnetic field causes a repulsion that instantaneously brings these things to a stop, and then they split back apart again. So what happens is kinetic energy must have been converted into magnetic field energy and then given back to the air track gliders. So there's another fundamental relationship between a mechanical system where we initially give two air track gliders some sort of push with our force, and then that energy that we use with our hands is converted into a magnetic field energy. The magnetic fields take our energy, store it for a minute, and then release it. Inductance is kind of the same sort of idea, except with a circuit and with currents. So that's sort of like some physical intuition for how magnetic fields can store energy. You can see how they can take kinetic energy and store it as magnetic potential energy, kind of like a spring. And that's what you'll see. The same analogy. They make an analogy between these magnetic inductors and springs. Because if these were two springs, the springs could compress and bounce off of each other in the same way, right? So the magnetic fields work a lot like a spring. And that's also why electric and magnetic fields, quantum mechanically, are treated as simple harmonic oscillators. You'll see in quantum field theory, the first thing you do is you try to write a simple harmonic oscillator as a quantized field. That's why, because electric and magnetic fields act like simple harmonic oscillators, except in a field throughout all of space, rather than like an actual spring. Anyway, that's enough for today. We'll talk more about how inductance works in circuits next time. Have a great Halloween.